I'm resisting efforts to make me dedicate this day to Mr. Rogers. It's not funny. Mr. Rogers did die last night, so what I want to do today is complete discussion of interval estimation. And let me just start that by summarizing, I think, the material that we've discussed so far. We have looked at two circumstances, one in which n is large and sigma is known, and one in which n is large and sigma is unknown. In both instances, we have been trying to estimate mu, the population mean. And while these two formulae differ in specific, the logic remains the same. And I think I've encouraged you to try and focus on the logic rather than the specific features of each formula. In each case, we estimated mu by, first of all, including in the estimate the point estimate, x bar, which offers, because the sample is random and because the sample is large, is an unbiased estimate of mu. What we then did was to establish some range of scores equally distributed around x bar that was some number of standard deviations, some number of standard deviations of the sampling distribution of sample means. It was 1.96 standard deviations when we were constructing 95% confidence intervals, and 2.58 standard deviations when constructing 99% confidence intervals. In the first instance, where sigma was known, the standard deviation of the sampling distribution of sample means was sigma over the square root of n, and in the second circumstance, where sigma was unknown, we used S as an estimate of sigma, but recognized that S was a biased estimate of sigma, and so corrected for that bias by including n minus 1 in the denominator rather than n. And we've gone through one example of that, as I recall. What I want to do first, then, is to go through a second example of this circumstance, and that is included in application 7.1 on page 166. In application 7.1, you are told that a study of the leisure activities, or as we would say, the leisure activities of Americans, was conducted on a sample of 1,000 households. That is, you know that n equals 1,000. The respondents identified television viewing as a major form of leisure or leisure activity. If the sample reported an average of 6.2 hours of television viewing a day, that is, you know that x bar equals 6.2, what is the estimate of the population mean? That is, what is the estimate of mu? And what you discover, if you look below, is that you're given x bar, s, and n. That is, you're given x bar, which we knew, 6.2. You're given n, which we knew to be 1,000. And you're given s, which is the standard deviation of the sample, and it is 0.7. Are there any questions about the first part of this scenario, the first part of this problem? Then the rest of it is really, first of all, understanding that you're in situation 2. You're estimating mu, n is large, that is, it's in excess of 100, and sigma is unknown. The estimate of mu, then, is equal to x bar, which is 6.2, plus and minus, and if you look through this problem, it does ask the 95% confidence interval. If the confidence interval is 95%, or the confidence level is 95%, then the z value is 1.96 multiplied by s, which is 0.7, divided by the square root of n minus 1. N is 1,000, so n minus 1 is 999. Are there any questions as to how we got from this general statement to the specific statement? No? Then it's simply a matter of keystroking from this point on. And according to Healy at least, if you perform this computation, the answer is 6.2 plus and minus 0.04. That is, you are 95% confident that, on average, Americans watch somewhere between 6.2 minus 0.04, which is 6.16, and 6.2 plus 0.04, which is 6.24 hours of television per day. Are there any questions at all about estimating mu? Either in situations where sigma is known or situations in which sigma is unknown. What I will do today is to post a series of problems dealing with interval estimation onto WebCT. As I recall, that would be assignment 5. So assignment 4 was the sampling thing, so this will be assignment 5. The remainder of the assignments have been deleted anyway, so it will be the only one there. It will include both of these circumstances, and those problems will also include the third and last circumstance that we will look at momentarily. But before we leave estimations of mu, let me ask again, are there any questions? Yes. Could you?
How did you get the 99 again? 999 from the top?
Because...
Never mind.
Well, you are, I know. You see where it comes from now, but I will answer the question. The question is, where did we get this 999 from? The denominator, we're dealing with a situation in which n is large and sigma is unknown, so that the denominator here is the square root of n minus 1, and n is 1,000, so that n minus 1 is 999. Yes.
From what I've looked at last notes and these notes, the 1.96 we've used in basically every example compared to the 99. Yeah. Is it more wise to use the 96 than the 95%? Or is it more accurate? I mean, you probably said this, but I'm just trying to make sure.
The question is really one level in observation that in the examples that I've offered, we've always computed 95% confidence intervals, so that the value of z has always been 1.96. The question is then really is that better than or worse than 99% confidence intervals? I don't think it's a question of better or worse. It's a trade-off. It's a trade-off between, on the one hand, increased confidence from 95 to 99%. And if we talk about that in terms of alpha, the likelihood of being wrong, the likelihood that the estimate will not include the population parameter, then the likelihood of being wrong decreases from 0.05, a chance of 5 in 100, to 0.01, a chance of 1 in 100. Those two observations would argue in favor of higher levels of confidence. That is, if choosing between 99% confidence intervals and 95%, we would choose 99% intervals because there's less chance of being wrong. The trade-off, however, is with the magnitude, the width of the interval. And this is relevant to a later discussion too. I presume that you understand that this section determines the interval around x bar, the width of that interval, so that as sigma or s increases, this value will increase, so the width will increase. As sigma, or the standard deviation of the sample, decrease, the opposite happens. The width of the interval decreases. As n decreases, the width of the interval increases, because small n's mean that this value, the standard deviation of the sampling distribution of sample means, is relatively high, so that the whole value is relatively high. If you have a large sample size, that if the denominator here, the square root of n, is relatively large, then sigma over the square root of n, or s over the square root of n minus 1, is relatively small, so that the interval around x bar will be relatively narrow. Another thing that affects the width of that interval is z. If you multiply whatever this value is, the standard deviation value is, by 2.58, you're going to generate a higher score than if you multiply by 1.96. And another way of saying that is you will generate a wider range of scores. That hasn't really been an issue in the examples that we've looked at. And it hasn't been an issue because these standard deviation scores are unrealistically low. So that what you generate is very narrow estimates anyway. 6.6 hours to 6.24 hours is a very narrow range of error. But in reality, when these standard deviation or variance scores are much larger, then these intervals become wider. And then the difference in multiplying by 1.96 or 2.58 becomes important, has important implications. That is, if you multiply by 2.58, if you adopt a 99% confidence interval, you can in fact generate ranges of scores that are so wide as to be essentially uninformative. So that's the trade-off. On the one hand is increasing confidence, less likelihood of being wrong, but on the other, you're simply generating wider and wider interval estimates, which at some point become uninformative, which is an argument for using lower levels of confidence, that is, lower z-scores, and the compromise is often 95%. It's certainly a convention used in the social sciences.
How do you determine if sigma is known or unknown, and is it important to know for our tests?
It is important to know. If I can answer the second part first, the question is, how do you know whether sigma is known or unknown, and is that important for the test? The second part of your question is easily answered. Yes, it is important because it determines which of these two formulae you use. If sigma is known, then you use this formula. If sigma is unknown, you use this formula. How will you know whether sigma is, how do you know whether sigma is known or unknown? It's simply a matter of it being in the narrative. In the narrative that you're given. Now, it's not in the narrative here because Healy separates out S. But I believe that we looked at an example on page 164. Is that right? In which, you see, the statement at the bottom of page 164, the sentence that begins average income for a random sample of a particular community is $35,000 with a standard deviation of $200. Clearly, that $200, like the $35,000, refers to the sample, would you agree? So that what you're given here is X bar and S. When you think, if you reflect on the first example that we looked at that was on page 163, and it dealt with the IQ scores of a particular community, you were told that the average IQ of a community, and it randomly selected a sample of 200 residents with a sample mean IQ of 105. So you're clearly being given the sample mean there, X bar. Assume that the population standard deviation for IQ scores is known, and you're given a value of about 15. Actually, you're given a value of 15. So, and clearly that score refers to the population and not the sample. So what you're being given here is sigma and not S. So the answer to the first part of your question, how do you know whether you have sigma or whether you have S, do you have the standard deviation of the population or of the sample, is that information is contained in the narrative, the narrative part of the question. Are there any other questions? Let's then look at situation 3. Situation 3 is a situation in which you're dealing with proportional data rather than integer data. What you're trying to estimate here is not mu, the mean of the population, but P subscript U. P is in pillock and U is in umbrella. P subscript U, simply notation for the population proportion. And the formula for computing that estimate takes precisely the same form as we saw in the other two situations. P subscript S, the sample proportion, provides an unbiased estimate of P subscript U, in the same way that X bar provided an unbiased estimate of mu. When n is large and when the sample has been selected randomly, P subscript S, the sample proportion, provides an unbiased estimate of the population proportion P subscript U. What we're now going to do is put around that, add and subtract, an interval. Now, the form in the first two situations was Z, some number of standard deviation, some score, multiplied by the standard deviation of the sampling distribution of sample means. Likewise, when you're dealing with proportional data, it's plus and minus Z, which again will be 1.96 or 2.58, multiplied now by the standard deviation of the sampling distribution of sample proportions. It's a different distribution, a sampling distribution of sample proportions rather than sample means. That's, I won't say that's incidental, but I think you should focus on what remains stable. And what remains stable is the form of the formula. The point estimate, the unbiased point estimate of the population parameter, plus and minus some number of standard deviations, where the number of standard deviations depends upon the confidence interval, 95 or 99%. Now don't gasp as I write this. The standard deviation of a sampling distribution of sample proportions is P subscript U. It's actually the square root of P subscript U multiplied by 1 minus P subscript U over N. And that's formula 7.3 on page 165. What is the problem here? What is the problem here? How can you solve this?
Well, we need numbers to plug into.
Well, you need numbers to plug into it. I will grant you that. But even if I gave you numbers, the numbers you would get would be what? P subscript S, right? Sample proportion. You would be told whether the desired confidence interval was 95 or 99%, so you could give a value to Z, and you'd be given a value of N. The problem is this numerator here. You're asked to give a value to P subscript U, which is the very thing you don't know, and are trying to estimate. Yes? And this is quite honestly where the semester comes to a halt. There's no way around this. We just close up shop and off we go home. No, some clever dick has solved this problem. We talked moments ago about the factors that influence the width of the confidence interval. One was Z, one was the numerator in the standard deviation value, and one was the denominator in the standard deviation value. Yeah? That is, we talked of three factors influencing the width of the confidence interval. Z, the value of Z, that is 95 or 99% confidence intervals, the value of sigma or of S, and the value of N. Let's focus on, well, we have no choice with regard to Z. If you're computing a 99% confidence interval, this has to be 2.58, and a 95% confidence interval, this has to be 1.96. You have no choice over N. If you've got 200 people in the sample, you've got 200 people in the sample. Right. What you do have a choice of is the value of P subscript U, because you have to give it some arbitrary value. Do you agree that as this numerator grows large, so the width of the confidence interval will increase? And as this numerator grows small, the width of the confidence interval will decrease. If you agree with that, and if you understand that, would you agree as well with a sort of sense that if you set this numerator to some value, some small value, you're cheating? You're arbitrarily narrowing the interval estimate. Yeah. The logic then in defining this denominator, in defining P subscript u, is to give it a value, give it the highest value possible. That is, be the most conservative possible. That is, to generate an interval estimate that is as wide as possible rather than as narrow as possible. Well, let's test this out. Let's suppose P subscript u is 0.9. You give it a value of 0.9. 1 minus P subscript u would then be 0.1, you agree? So that the product of those two scores would be 0.09. If you set P subscript u to 0.8, 1 minus P subscript u would be 0.2, and the product would be 0.16. If you set P subscript u to 0.7 and 1 minus P subscript u to 0.3, the product would be 0.21. 0.6 and 0.4, the product is 0.24. 0.5 and 0.5, the product is 0.25. Now as you start going to 0.4, this would be 0.6. You're simply doing the computation in reverse. You agree? You're multiplying 0.4 by 0.6 rather than 0.6 by 0.4. So here we would have 0.3 and 0.7, 0.21, and these values then would go back down to 0.09. Yes? So the highest value this numerator can assume, would you agree, is 0.25. And that occurs when you set P subscript u equal to 0.5. Are we all agreed? Yeah? Hence, rather than commit this frightening formula to memory, what you should commit to memory is that in this circumstance 3, where you're estimating P subscript u, the way you do that is to start with P subscript s, the unbiased point estimate, plus and minus z multiplied by the square root of 0.25 over n. And I'm only going to say this once. It is always 0.25. It is always 0.25. I said it twice. It's like the Spanish Inquisition. The two major assets are their surprise, their ruthlessness, and their dedication. Okay, there are 3 major assets. This portion will always be, this is 3 times, 0.25 over the square root of n. I'll answer a hypothetical question. Dr. Douglas, are there any circumstances under which the numerator is not 0.25? No, there are not. It is always 0.25 over n. So that the formula is P subscript s plus and minus z multiplied by the square root of 0.25 over n. I think I've said it 7 or 8 times. It is always 0.25. Yes.
So for number 3, is that the new formula?
Is that the revised formula? As
Yes,
opposed
the
to the
revised.
one in the text or the one that we
The
started
first
with
one.
here?
Yeah, it's the first number 3.
This,
The same one?
does it look like the same?
Well, no, it's not. I know it's not the same one, but
Does it look similar?
yeah.
What's
Yeah.
the difference?
We have a 0.25 over.
rather than P subscript U multiplied by 1 minus P subscript U, I have 0.25. And that's because it is always 0.25. So the answer to your question is yes. This is a revised version of Formula 7.3. If we take a look at an example, and this is a situation that should be most familiar to you of all three, because this is the political polling situation. Yeah. The example that begins at the bottom, the last paragraph of page 165. To illustrate these procedures, assume that you wish to estimate the proportion of students at your university who missed at least one day of classes because of illness last semester. Well, that's 100%. And I want to know, where do you get those doctor's forms from? You know? It's a giveaway when you talk in the first person on those notes. I have been sick. Oh, Stephen has been sick for 3 days and could not come to class any of those days. Don't talk in the first person on those. It is a giveaway. Anyway, back to the theoretical problem. Out of a random sample of 200 students, n equals 200. 60 reported that they had been sick enough to miss classes at least once during the previous semester. And you're asked to compute the proportion of all students who missed at least one day of classes because of illness. What is the value of P subscript S? Pardon? You can't, if it's a proportion, it has to assume a value between 0 and 1. For those of you at home, the answer was 60. No, that's not the answer. That was the proposal over here, that P subscript S equals 60, and I said no. P subscript S is a proportion, and so must assume a value between 0 and 1.
Wouldn't it be 60 divided by 200?
It would indeed be 60 divided by 200. Where do you get the 60? First of all, where do you get the 60? At the very bottom of page 165, it says, out of a random sample of 200 students, 60 reported that they had been sick enough to miss classes at least once, and so on. So P subscript S equals 60 over 200. This is important. When we were dealing with estimates of mu, those estimates relied on, first of all, the unbiased point estimate x bar. And x bar could be presented in only one way. You were told that the sample mean was 5.2, or the sample mean was 35,000. That is not true of proportional data. P subscript S, most obviously, could be presented as a proportion. We could have been told in this instance that 0.30 of the sample had missed at least one class. It can appear as frequency data, which we have. You can be told that 60 out of 200 persons did something, or 55 out of 412 did something. Or you can receive the information in the form of a percentage. And we could have been told that 30% of the sample of 200 had missed at least one class because of illness. However you receive this information, you must transform it into a proportion. because that's what the formula calls for. Are there any questions about this issue of how P subscript S, the sample proportion, can be presented, and how you go about converting that to a proportion? Are there any questions then about this specific instance?
If we're following the later half of the formula of the 0.25 over n.
We haven't got that far yet.
Okay, because I'm seeing the 200 in that place, so I was thinking.
We haven't got that far yet. The question was asking about the 0.25 over n, and I'm not cutting you off. We'll get to that. Yeah, I'm concerned at the moment as to. I could do a puppet show. This is a hand. Doesn't look at all like my hand. I'm concerned only at the moment that we understand how to determine P subscript S.
So it's more of the formulas just having this look somewhat similar. We're taking the 60 over the n to get the P subscript S.
It's not anything about the formula looking sort of similar. The formula does require that you input P subscript S, the proportion of persons who did something in the sample. I've simply indicated to you that unlike mean scores, that information can be presented in any of three ways: as a proportion, as a frequency, some number out of some number, or as a percentage. Regardless of how it's presented to you, it has to finish up. You have to convert it into the form of a proportion. We then have plus and minus, and you are asked to compute a 95% confidence interval. So the z value is 1.96. Yes. Multiplied by the square root of 0.25, because it's always 0.25, over 200, which is n. Yes. Are there any questions as to how we got from this general statement to this specific statement? No? Then it's simply a matter of running through this computation. 60 over 200 is 0.3, let's say 0.30, plus and minus, and if you do this part of the computation, at least according to Healy, and Healy's not always right, plus and minus 0.07. That is, you're 95% confident that in the population of students, somewhere between 0.30 minus 0.07, which is 0.23, and 0.30 plus 0.07, which is 0.37, of students missed at least one day of classes because of illness. This information is more commonly presented in the form of a percentage, so that we could talk about 23% to 37%. Two observations, and then I'll take whatever questions you have. One is that when you hear this sort of information presented to you in the media, what you would be told is that the research conducted on absenteeism, class absenteeism, indicated that 30%, the point estimate, of students miss class at least once during a semester because of illness. The margin of error was plus and minus 7 percentage points. This is, my second observation then is, this is a fairly substantial margin of error. Your answer, you're now 95% confident that somewhere between 23% and 37% of all students missed at least one class due to illness. That's a pretty substantial margin, 23% to 37%. And here is the answer to your earlier question. If we were now to, instead of using a 95% confidence level, use a 99% confidence level, this value, of course, of z would go to 2.58, so that this value of the error value would be approximately 0.1. And then we've got a margin of 20 percentage points. And at that level, I think you say, is this estimate meaningful? Does it tell me anything very useful? And I think the answer to that is perhaps no. So it's a trade-off between increased confidence in your estimate and the usefulness of the estimate. The trade-off between the confidence of the estimate in the estimate and the usefulness of the estimate. Are there any questions about dealing with proportional data or interval estimation in general? I will take that as a no. Again, I expect at the end of the semester, when you're asked how clear were the instructor's explanations, you will say, crystal clear, crystal clear. I got them first time, every time. So. Then just two observations. One is to remind you that I will load onto WebCT when I get back to my office a series of test problems that will include all three situations. And the only other thing I have to say is enjoy spring break, and I will see you next time.